We went over radical expressions last week. That won't show up on the test or quiz. We went over radical equations that will. Now we're going to start on graphing radical functions. You're still going to see the equal sign that you saw on equations. You're still going to see a variable underneath a radical like you saw last week. Now we're just throwing in a y. Because of that second variable that introduces the second axis, x and y axis, now we can graph. I'm going to go a little bit above what's going to be on the test and quiz, just because morally feel the obligation or ethically I feel the obligation to. I haven't seen the test yet, but I have seen the quiz. This is the only type of radical that I see that shows up on the quiz, which is the square root. But I'm also going to show you how to graph cube root, which logistically is almost the same thing. The steps are the same. The method that we use for graphing radical functions is to use transformation. You should have done this already in Algebra 1. Now, the way that you went about it might seem different. It's the same thing. Each teacher might have their own little twist that they put on it, but at the end of the day, we're doing the same thing. I like to use a formula that does all the work for me. And all I gotta do is plot the point. Some teachers might more of a kind of a practical approach where you can actually kind of see the points. I'm going to use kind of that. I think that covers more of the things than anything else. To some degree, these graphs are going to be sketches, but I would say that they're not sketches as much as like polynomial functions and rational functions. Now, what do I mean by sketch? Yeah, that they lack formality, that they lack precision. They're going to be precise enough. Now, what they won't be as precise as is like a line. What back in the day when we first learned how to graph lines, what do we use in order to graph lines? Well, close enough. Yeah, actually, I couldn't get that answer out of the first period, but you would use a slope. Plot 1 point down, you use a slope. I'm up for 2 points, 3 points, however many you want. And then you have a tool known as a straight edge that would take care of business for you, and wham and bam, it was pretty darn precise. Since radical functions have a curvature to them, in that respect, it's going to be a sketch. You don't have like a curve tool that's going to help you curve your lines, but we should be able to have enough points where it's fairly precise. Like it's going to be hand drawn, but you're gonna have some points to guide you. What I'm going to ask for is for square roots. Let's try to plot 4 points. What you see on the board right now is known as a parent function. What a parent function means is that the only operation that's occurring to the x is a square root. You might want to write this down. I don't have it there written for you, but square roots have a restricted domain. What types of numbers will not give you an output if you put them into a square root? Yeah, which is why we start at 0, and if you can look at the drawing there, there's an endpoint on the drawing. But that's actually one of the first things you realize is that square root functions, when you graph them on one side, it will end. On the other side, it will go forever. There's only one arrow. That changes for cube. What's the square root of 0? 0. If I were to just keep on going, what's the square root of 1? 1. Square root of, what should I put next? 2? What should I put next? Yeah, square root of 4 is 2. Let's put our perfect squares. 9 is 3, 16, 4. These aren't the only points. There's an infinite amount of points here. But as far as integers go, they're easy to plot. 25, 5. Man, we'll come next. 36. Man, 36, 6, good. 49, 7, 64, 8, 81, 9, 100. Okay, we'll come next. All right, keep on going. I'm going to stop it. Oh, close. Yeah. 121, good. And then that'd be 11, yeah. So think of these as starting points. Because now what's going to happen is we're going to put some numbers around the x. The x is the input. And that those numbers will affect the appearance of what this is what it would look like if I was only taking the square root of the x. But depending on what numbers I put around, I could get that shape and I can stretch it, I can compress it, I can flip it, I can slide it. Things that you should have already seen in Algebra 1 with the parabola. We use the same method to graph parabolas. I'm going to use a formula to do all the work for me. You'll see that at the bottom of the page. But since some of the questions might be phrased asking you what type of transformations occur, these are the transformation numbers, the values, and what transformation they perform. So first of all, A. Where do you find A? Where is that A located?
Outside.
It's the coefficient of the radical. Yeah, it's going to be outside, sure. Okay. What A is in charge of is vertical stretching and compressing. If A is greater than 1, you're going to see that basic shape that you saw above there get taller and skinnier. If A is between 0 and 1, what types of numbers are between 0 and 1?
Fractions.
Okay, proper fractions. Yeah, then we're going to see that shape get short and fat. What types of numbers did I not discuss? Negatives. If A were to happen to be negative, what would happen is a flip, and I should be more specific here. It's going to be an x-axis flip, an x-axis reflection. You can write that. And that would occur if the A was negative. You would get this shape, and it would start to look like that. Here's a value that you did not see with parabolas, which is C. Where do we find C? Where do you find C? Where is that C located? Well, the main thing to cue in on is that it's inside the radical. Then as Caroline said, you can say it's before x, it's in front of x, it's the coefficient of x. Some people might focus on the fact of the parentheses, but the parentheses are only going to be needed if that C is greater than 1 and if you have an h, if you have a number coming afterwards. But the key is that the C is in front of the x. And in many ways, C does the same things that A does, which is why, like for parabolas, you weren't even introduced to C. I haven't seen an Algebra 1 yet, regardless of where I've taught that even introduced to C. You learn A, H, and do you guys remember A, H, and K from parabolas? Mm-hmm. Now the reason why, see, because like, see, if I get a parabola, right?
We see the H and K and then surface Q.
For circles, no, circles just had H and K. There's a circle, and then what took the place of the A was arcradius. They've done that last year. But yeah, I was trying to make a way to make this like look, skinnier and fatter, but it won't let me. It won't let me make it. If I try to dilate this, it's gonna do it proportionally. It's not gonna let me do it. It's not gonna let me change the proportions of it. But if I get any shape, and let's say vertically, I make it taller. Even though I'm not doing anything horizontally, what is it going to appear is happening horizontally? Not stretching, not horizontal. If I stretch something vertically and make it tall and skinny, if you're a little short, stocky kid when you come into 9th grade and you hit a growth spurt and you get taller, okay? Even though you may have not tried to be losing weight, you're gonna look like you're gonna, what? Yeah, you're gonna look a lot skinnier too. Horizontally, you're not gonna look as wide. If you get something vertically and you switch it and make it shorter, even though you're not actually trying to affect it horizontally, what's it gonna look like? It's gonna look like it's also getting wider. And that actually still even applies here. Even for square roots, that still applies. But the only reason why C needs to be introduced for square roots is because of this. And if you want to, you can probably write this in. This is a y-axis flip. So like with a parabola they did back in Algebra 1, if I were to get that parabola and flip it horizontally, flip it over the y-axis, what's it going to look like? 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 Do I get a parabola and flip it? If I flip it on the y-axis, I literally just did it. It's the same, yeah. I realize this is hand drawn or whatever, but yes, why? Because parabolas are symmetrical. So that's why you weren't introducing to C. But look, if I go up to a square root and I flip this across the y-axis, guess what? It's gonna look different. It's actually the only way that you can get the arrow to point left, opposed to the right. That's why you need to know about C. H and K are our good old friends. They were here back when we did parabolas. They do translation. Those are the numbers that are going to slide whatever your drawing is around the page. And a very common mistake occurs with H when it comes to identifying H. What does H have in front of it that none of the other numbers do? A negative. So when you think you see H, it's actually the opposite sign. If inside there I see X plus 7, well, H is actually negative 7. Same thing, vice versa. On every single graph that we do, we are going to identify AC, H, and K. Again, before I move on, understand the basic shape here. They're always and this really applies to any even index, but we're only going to graph square roots as far as even indexes go. One endpoint and one arrow. Even though we don't have to graph this, and fine, I'm not going to emphasize it, but I'd be remiss if I didn't introduce it. I think it's something that needs to be taught. Are cube roots. Unlike square roots that have an even index, there is no restriction on the domain. There is no way to get an error if you hit the cube root button on your calculator. If you take the cube root of any real number, you're going to get a real number. And because of that, now we have two arrows. The transformations are going to be the same. A is going to do the same things. C is going to do the same things. H and K are going to do the same things. And they're going to be found in the same location. The only thing that changes is the starting shape. If you were just to use basic words that anybody on the street would use, what could you describe a parent cube root function as looking like? If all I did was take the cube root of x, what does that shape look like? Huh? Like a Z? I like that you're using a letter. It looks like that, so I think most people would look say it looks like an S that's a little squishy. That doesn't look like an S to me. Well, it's fine. If you want it to be technical, yeah, see, the problem with an S is that an S would fail a function test. It would fail a vertical line test. But if you suspend disbelief, it kind of looks S. Now, I put some parent points up there on the graph for you, but let me also list them for you in a table format. I'm sorry. Before I just thought of something else. Just another thing you might want to understand going forward. So here the endpoint, you see how it's 0, 0? Once we transform it, like we're never going to use 0, 0 in order to transform, because 0, 0, 0 is always going to end up being H and K. And the same thing here. Notice how 0, 0, like if I take the cube root of 0, what do I get? I get 0 also. 0, 0 is going to also end up being h and k when we transform. The difference is that on this, it's not an endpoint. There are no endpoints on the cube. What are some common points? There's an infinite amount of points for you to use, but some common ones that I like to use, I'd say negative 125, negative 5, negative 64, negative 4, negative 27, negative 3. Negative 8, negative 2, negative 1, 0, 0, but that we're not going to use because it's going to become HK. 1, 8, 2, 27, 3, 64, 125, 5. Okay, we've already gone 1, so we're not going to get this there. Is that what you're doing? We'll go next. It should be 216. 6 to the third. Okay. 343 will go with 7. I'm not sure. 8 is 724. What's 8 to the third power? 512. Okay. And here we go. Without further ado, here is the formula that we've been talking about. So I gave you two tables. Once we identify the type of function we're graphing, more of them are going to be what? Most of the ones we graph are going to be square root, because that is what's going to show up on that Lisa quiz. We're going to get any one of those x's, and once we've identified a, c, h, and k, we're going to get the x and divide it by c and add a and add h. C and h correspond to x. We're going to get the y that goes with that x, and we're going to multiply it times k, add k, and by O our graphing transform. Now, if you look at your packet, the first page and a half, 2.5 pages, to me are more kind of like a student-led type of thing. If we have time, and I see maybe something I'll go over it again, if I see anything good there, maybe I can go back and touch on that. A lot of what we do tomorrow will depend on how much we got through today. Now, since I already had a period, I don't know what we're going to get to, but what I wanted to do was start on the bottom of the third page. Like I want to start already with, let's just jump right into graphing. First thing we want to do is identify the type of function. What type of function is this? Shout it if you know it. Square root. That's important because that's going to tell us where to find our parent points. That's the one we're going to do most. That's the one that are going to most likely show up on the assessments. But after identifying the type of function, let's go ahead and identify the transformation numbers. A, C, H, and K. What's the A here? A can be found out in front of the radical. And if I don't see it here, it's a 1. What's C? C can be found inside the radical but in front of the x. So both A and C are coefficients. A is the coefficient of the radical. C is the coefficient of the x. And in this case, they're both 1. Strangely enough, especially if you like to take shortcuts and you feel that you have a good understanding of this, anytime either of these are 1, you can ignore them when it comes time to transform. Because if you go back and look at the formula, look at the operations, what operation am I going to end up doing with A? What type of operation am I going to end up doing with A? What operation, operación, add, subtract, multiply, divide, what am I going to end up doing with A? No, I don't divide A. Look at the formula on the first page. What am I going to do with A? I'm going to multiply it. What's anything times 1? Huh? It's itself. So, hey, I get it. Something's going to change there. How about C? What operation do I end up doing with C? No, C does not get multiplied. It gets divided, but hey, what's anything divided by 1? also itself. So, like on this particular graph, A and C aren't gonna do anything. I'm gonna use them because it's partly because I know you're half asleep. I think it's a good start, but eventually, when that occurs, I'm gonna just skip. If A or C or one, I'm gonna skip. What's my H here? H can be found inside the radical. It's being added or subtracted. H can be found in the radical. One person said it. Zero. H here is going to be 0. Inside the radical, nothing is being added or subtracted to the x. 0 is the additive identity. Strangely enough, if you go back and look at the formula, what ends up happening with H? What operation do I end up doing with H? I end up adding it. So, the same way like with A and C, that you can ignore them if they're 1, H and K, you can ignore them if they're 0. So I'm going to end up ignoring H on this one. I won't do it on the first one, but that's what we'll do. And then how about K? What's K here? K is going to be -2. Whoa, whoa, whoa. You told me that we have to change the sign. That's what we are doing. If you see it, you should change the sign. That would be okay, so now let's go ahead and let's pick our let's find our points. What points are we going to grab? We know that square root functions have an endpoint. And maybe didn't emphasize it as much as I would have liked, but I did kind of squeeze it in there when we were on the first page. Where can you always find your endpoint? Well, it starts at 0, 0, but where does it end up at? I went back and I had started doing cube roots. I'm like, oh wait, let me go back and I pointed something out to you. Starts with an H and ends with a K. My H is 0, my K is -2. I'm going to have an endpoint as 0, -2. Now I need to find some other parent points to transform. I just can't use 0, 0. What you see on the board there came from 0, 0. Pick any of the other points I gave you on the table. Unless I start seeing fractions or, like for instance, C, because C gets divided, then you might have to be aware and be creative if you want to try to avoid fractions. But I don't see anything here that would cause for concern. I want to keep my graph as small as possible. I'm going to use 1, 1, 4, 2, and 3. What do all of those points have in common? Well, the x's are perfect, meaning if I take the square root of each of those x's, what do I get? The y that's right next to it. Now that I have these points, let's go ahead and apply our transformations. What am I supposed to do? What am I supposed to do with the x's? Look at the formula. Highlight it, do whatever you want, write it big on a sheet of paper. I'm not going to write it for you on the quiz. You can memorize it. Not that hard to memorize. What do I do with the x's? Divide C and add H. Well, look, it's it. On this one, I told you it's not going to make a difference. But the first one, let me just put it out there for you. Okay, so this is the x I'm starting with. I'm going to divide it by C, which is 1, and add H. What's 1 divided by 1 plus 0? Still 1. Nothing's going to change. This one would be 4 divided by 1 plus 0. This would be 9 divided by 1 plus 0. What's going to happen to the y's? Okay, they're going to move times what? Times A, and then plus K. So this y here is a 1, and then times A, which happens to also be 1, and then plus K, but K is negative, so minus 2. 2 times 1. I don't normally recommend to do all the points at once. I would just go 1 point at a time, but I'm just trying to emphasize the point. 3 times 1 minus 2. Just want you to see that we're doing the same thing to all these points. The points themselves are different, but we're applying the same transformation to all of them. Now let's do mental math. let's go 1, and this is -1. This is 4, and this is 0, and then this is 9. Guys, can you see where I got those numbers from? I'm not confusing you. All I do is I perform the operation. Now let's see what this would look like. Let's plot our points. 0, -2. Another thing you're gonna see, there's gonna be problems where you're actually not gonna have to graph. They're gonna just tell you, hey, what transformation is being performed. If I told you A and C are not gonna have an effect of the 1, you can ignore it. H is not gonna do anything to 0, you can ignore it. The only transformation here is K. What does K normally do? What type of transformation does K do? Also on the first page, as the arrow pointing to it. What does K do? Like, how does K affect the appearance of vertical what? Translation. And since K is a 2, where translation just means move or slide, where is this going to slide? Down to. If I look at my final product, once I finish graphing it here, once Alexis finishes graphing it on her paper, it should look exactly like what I have here on the first page, just it's going to be 2 units below. The same starting point. But what gets out at the end is going to be different depending on AC. So 1, -1, 4, 0. And also let me be clear. When we say same starting points, what you see in black here, like you get to pick that technically. Okay, like there's an infinite amount of points to pick from. I think I gave you 10 for each function. The reason I like to pick the smaller ones possible because it keeps my graphs. Well, like you're gonna see what I don't know if we'll get to it today, but there's one like where I strategically pick numbers because I want to avoid fractions. It's up to you. Okay, so now I see 4 points. That's going to give me a good enough definition of the curve, but on the square root, just as important is knowing square roots have one endpoint and one arrow. So if you do this, don't write this, don't write this, don't write this, don't write this. You could have the correct points, but if you do that, it's wrong. Because we specifically know that the endpoint has to be the one that's at 0, -2, and then you connect the dots. Any questions? All right. This one. What type of function is this? What type of function is this? It is a square root function. That's gonna decide the types of parent points we pick. But before we do that, let's go ahead and identify our A, C, H. Okay. What is A here? It is 1. It's out here in front. What's C? Also 1. Whoa. But you told me that when there's another number there, and there's supposed to be a parentheses. I'm so confused. That not when C is 1. In order for there to be a parentheses, C would have to be something other than 1. And then, yes, you'd have to have another number. C is just 1. What's H?
4.
-4. 4 with H, a very common mistake, even for the smart children. They forget to change the sign. Don't do it for K, but I do it for H. Why? Who remembers why I explained to you why he has to change the sign? Because in the formula, H is the only one that has a negative in front. What's my K value here? 0. So now to start saving time, What I'm going to do is I'm going to ignore any transformation that's not going to have an effect on that specific graph. Here, based on our transformation values, which is the only transformation that's going to have an effect on what this graph is going to look like. H. If A or C are 1, you can ignore them. If H and K are 0, you can ignore them. So I'm gonna apply the 4 for H. What does H do?
Transitions we looked at them, right?
Horizontal translation. So since H is positive 4, where is it going to moving? Yeah, but instead of me showing you how the graphic, it's on the board and show you how it moves, I let the formula do the work for us. So we're going to have an endpoint. Where's the endpoint going to be? Yeah, it's HK, 40. And now I need other starting points to transform, to apply the other formula, like the transformation formula. So I would look out for fractions, and I would look out for C. If there's no C to worry about, if there's no fractions, let's keep our graph small and just do the same 1, 1, 4, 2. And then unlike the first one though, you're not gonna see me put every number in there. I'm only gonna put the numbers that are having an effect. How do I apply H? What operation is H gonna do, and to what am I gonna do it to? What am I going to do with H? And what am I going to do with 2? For that first page. What? H does not do subtraction. It does do addition. And what am I going to add it to? Look at the formula. The X. So all the X's. So I'm going to go get all the X's. And I'm going to add 4 to them. 1 plus 4, the Y is going to stay the same. 4 plus 4, 2 is going to stay the same. 9 plus 4, the 3 is going to stay the same. So this gives me 5, 1. This gives me 8, 2. And this gives me 13, 3. So another skill that the powers that be said that I need to teach you is how to scale. So let's say that what you're trying to graph does not fit in the space that you're allotted. That's fine. She's not here. You can change your intervals on the axes. Like right now, what am I counting by on the X and Y axis? By 1, yeah. And that's just because it was pre-printed. You don't need to be writing all that stuff like 1, 2, 3, 4, 5. Just it was happened to be pre-printed on what I pasted there. Just because you scale one axis does not mean you have to scale the other. Look at the points I'm going to try to plot. Look at the range. What's the range of the points I'm trying to plot here? Range means Y. What's the range of the Y's that I'm trying to plot? What's the lowest Y I'm trying to plot? No. 0. What's the biggest Y I'm trying to plot? 3. Is there going to be any point fitting that in the space I'm being given? No. Look at the X's. The smallest X is 4. What's the biggest X? Yeah, I don't have enough space to fit the 13. There's a few things you can do. Like, I mean, if you had the ultimate flexibility, I could just change and make like that quadrant bigger and get it to fit and still count by 1. But just to get some practice, let's change the scale of our X. Instead of counting by 1, what would be maybe another number that we could count by? To get 13 to fit. Yeah, it's count by 2s. You don't have to write it every single line, but if I'm counting by 2s, then at 5 I would have really 10, and at the 10th line I'd really be at 20. Same thing going in the other direction. You could do the same thing to the Y's if you wanted, but just you don't have to. All my Y's are going to fit. All right, let's plot 4, 0. Now on this scale, that means that the 4 would really be where the 2 is. On your paper, you probably can't even see those numbers anyways. So that would be the first one, 4, 0. 5, 1 would be then half a box over. but a full box up because I didn't change my Y scale. My Y interval did not change. 8-2 would be where the 4 is, but then 2 up. And then 13-3 would be in between the 6 and the 7. And then 3 up. Because I changed my scale, this graph is going to look a little bit taller than it should normally. It did not stretch at all, just since I changed my scale. That's what's going to make it look a little bit taller. And a why the worry face. You don't know how I'm dividing by 2s. I'm dividing by 2, 4, 6, 8. What do we appreciate? Hannah. Yeah, I didn't need to. You could have if you wanted to. I just didn't need to. But look at the Y's on the body. 0, 1, 2, and 3. Those fit. But if you want to be my guest. Just because you change one axis, you don't have to change the other. Questions? Thomas? No. Ooh. What type of function? Square root. So we're going to have that same basic shape. We're going to have our same starting points. But left side, it looks like we're going to have some more transformations here. What's my A here? 3, good. What's C? 1, yeah, because on in front of the X on the inside is a 1. What's H? -2, good. And what's K? -4. Which transformation values are going to have an effect on the appearance of my function? A, H, and K. I can safely ignore C, but A, H, and K are going to have an effect. Let's go through each one and talk about what each one is going to do. If you were to go to that first 2.5 pages of the notes, that's kind of what it's asking you, like it's that student event thing. It's just asking you about what each number is doing. So what is A going to do here? With an A value of 3, what's going to happen? It's going to be a vertical stretch. A is greater than 1. A also does things vertically. It's going to be a vertical stretch by a factor of 3. If you remember, I know it might seem like forever ago, but if you remember algebra 1, it's kind of weird to do algebra 1. The starting shape is different. How about H? What's H going to do? Horizontal translation in what direction?
Left.
Since it's negative. Left, how far? 2. And then how about K? Vertical translation in what direction?
Down.
Down, how far? 4. But instead of me, saying, hey, start with this shape, and then move it across the page, I find that to be more confusing, especially when it comes to the stretching and compressing. Sliding is easy, but the stretching and compressing can be confusing. So what does that formula do the work for us? I know that these have an endpoint. Where is this endpoint going to be? -2, -4. It's always going to be at H, comma K. That counts as a transformation of that 0, 0 number. If I don't see a fraction and if I don't see any type of a C, then I can just keep my graphs going to 1, 2, and 9. What's going to end up happening to all the X's here? All I got to do is subtract 2. Because the C is not doing anything, so all I do is 1 minus 2. 4 minus 2. I don't advise you to do all the points at once. I would just do one at a time. But this is more just for dramatic effect. Just to show you that the same thing is happening to each one. Right, Juan? Yes, sir. How does your paper smell? Good. I use fragrant paper. I think yours is supposed to smell like a wood. Always smells like summer breeze. Candle smells like M&M's. That's why I always try to trade. What's going to happen to all the A's? They're not going to stay the same. My brain was thinking one thing, my mouth said something else. What's going to happen to all the Y's? times all the y's. It happens to all the y's. They're not going to stay the same. What's going to happen to all the y's? Look at the formula. Multiply times a, which is 3. So I'm going to get all the y's there. Multiply them by 3, and then? Yeah, I'm supposed to add k, which is negative. I'm going to subtract 4, yeah. So 1 times 3 minus 4. And then you can start showing off your mental math skills. 2 times 3 minus 4. 3, which is the y here, times 3 minus 4. So this is, let's see, this would be negative 1. This gives me 2 and 2. This gives me 7 and 5. Take that mental math. All right, so now let's start plotting. Is there any need to change my scale here? Do I have to change any of my axes? No, it looks like every value here should fit in the space allotted. So negative 2, negative 4, negative 1, negative 1, 2, 2, and 7, 5. Oh, Mr. My points are correct and you marked them wrong. Just as important as getting the right points is knowing what direction the graph is headed. So since the end point here is negative 2, negative 4, the arrow's going. Unless C is negative, these are all going to go to the right. The end point would be on the left, and the arrow would be on the right. Questions? Wow, wow, wee, wow. What's different here? As a cube root, every step that I have done is going to be the same. The only thing that's going to be different is the final product. It's just going to look different. What are some differences between a cube root and a square root? The biggest difference.
The sign.
As far as the appearance of a graph, look at that first page. It's a parabola. Well, that's kind of there's no end point. This has 2 arrows. There's not going to be an end point. And because of that, because now we have to account for more space, I'm asking you to put 5 points. If you put less, it could actually end up looking like a straight line. But just like before, we're going to identify A, C, H, and K. What's my A value here? 2. What is C? 1. Yes. What's H? Positive 1. And what's K? Negative 4. I do not have an endpoint here. I don't have a C, which is good. I don't have a fraction. So the most common points I use for cube roots, unless I have to make some adjustments, are going to be negative A, negative 2, negative 1, negative 1, 0, 0, but 0, 0 is going to end up turning into HK anyways. But I don't want you to see it. And then these are just the most common ones I use. What? Where'd you get those numbers? You just make them up? My favorite number is 7. Can I just use 7 instead of 8? Where did I get all those numbers from? If I take the cube root of the x, what do I get? The y. All those numbers, if I take the cube root of the x, I get the y. I gave those to you in a table on the first page. Write it down. Now, once I have these starting points, I'm going to apply the exact same formula. Which of those transformations are going to have an effect? A, H, and K. H doesn't have an effect if it's 0. H is 1. So now let's look at the x's. What's going to happen with all of my x's? All you're going to do is add the 1. Because, yeah, the x's are supposed to be divided by c, but c is just 1. So I'm going to go negative 8 plus the 8, which is 1. Negative 1 plus 1. 1 plus 1, 1, 8 plus 1. And then, what do I do with the y's? Times a, and then plus k. So I get the negative 2 that I'm starting with, times a, which is 2. K is negative, down 4. Negative 1 times 2 minus 5, 0 times 2 minus 4, 1 times 2 minus 4, and 2 times 2 minus 4. Time to show off my mental math skills. Negative 7, 8, 0, 6, 1, and negative 4. Coincidentally, look at that. What did that 0, 0 end up turning into? No endpoint. No endpoint here. What did that end up turning into? H and K. Yeah, end up turning into H and K. 2, negative 2, 9. Then I'll plot these points. Few will not be on the test, but partly because the steps are the same, then why not? The only thing that's going to end up different is that it's going to end up looking like a different shape. And from the little time I've been in here doing that, just because it doesn't show up on one of our test quizzes doesn't mean it's not going to show up on the midterm or the final. So, right? I'd rather show this to you now than have to scramble at the end. Trying to show you. That's fine. Because the more points you get, the more definition you get. There's an infinite amount of points. You can do more than 5. But the thing is, if you were to do less, you probably wouldn't do 4. Because see, this point here, this H and K, even though it's not an endpoint, it's kind of like a point of inflection. It's where the graph becomes its steepest before flattening out again. And so normally what happens if you didn't do 5, you would just do 1 point on each side. You do 3 points. Those points are going to line up. People are going to think it looks like a line, but you're not going to see the curve. So that's why I say 5. 3. 6. 1 negative 4. 2 negative 2. You like watch, but let's pretend that, hey, I want to keep my graph really small. Can I just graph only 3? Those 3 points are these 3. They look like a straight line. But now by adding those extra points off to the sides, 9, 0, and what I already did, now you see a little bit more of the curve. Any questions for me? SF, calm down. I'm too excited today. We'll continue tomorrow with our Wednesday. That's